Hey, Itzik, Lior here. I wanted to put together this quick explainer for you, kind of my developer to developer take on how all these modern AI systems actually work under the hood.
We're going to keep it pretty technical and fast-paced. Hope this helps. Hey, so if you're a developer who's been working with LLMs, this one's for you. We're going to do a fast, focused deep dive into how modern LLM systems actually work from end to end. And we're starting right at the foundation, the low-level runtime view. Like, what is actually happening on the GPU to produce every single token?
All right, let's jump right in. We're talking about LLM inference, but specifically from our perspective, a developer's perspective. We're going straight under the hood to see the machinery that actually powers these incredible models. So here's the game plan. First, we'll nail down the absolute core concept of what an LLM even is. Then we'll touch on how models are made, just enough so we can really understand that crucial difference between training and inference. From there, it's into the deep end, the GPU runtime. We're talking weights, the KV cache, all that good stuff. Then we'll follow a single request on its entire journey through the system, and finally, we'll wrap it all up and see what's coming next. Okay, let's start at the very beginning. What is an LLM, really? Well, when you strip everything else away, it's all about one simple, powerful idea, predicting what comes next, one little piece at a time. You know, at its heart, an LLM is really just a neural network that has one job, predicting the next token. A token, by the way, is just a chunk of text. Could be a word, part of a word, even a punctuation mark. And the whole process is this incredibly simple, yet powerful loop. You give it some context, the model spits out probabilities for every possible next token, it picks one, tacks it onto the end of the context, and then it just does it all over again. That's it, seriously. Everything else you see, code generation, what feels like reasoning, it's all built on top of this one fundamental loop. And this is so important. This slide shows you what the model actually sees. It doesn't see letters or words like we do, it sees numbers, these token IDs. Tokenization is that critical bridge that translates our human language into a sequence of integers the model can understand, and then it translates the model's numbers back into words for us.
And this has two really practical consequences for us as developers. First, everything you send to the model, your prompt, your tool schemas, any context you've fetched, it all gets crunched down into tokens before the model ever lays eyes on it. Second, and this is the big one, tokens are the real unit of currency here. When we talk about cost, latency, or a model's context length, what we are always talking about is tokens.
Okay, so we get it. The model predicts tokens. But where does the model itself even come from? Let's take a quick second to draw a clear line between creating the model, which is training, and actually using it, which is inference.
Now, don't worry, we are not going to get lost in the weeds of training, but here's the 60-second version. Training is a cycle. You do a forward pass to predict a token, you calculate a loss by seeing how wrong you were compared to some real text, you figure out which way to adjust things with gradients, and then you update the model's weights to be just a little bit better. You do that billions of times. And the goal is always that same thing, get better at next token prediction.
You really don't need to memorize optimizers or anything like that. The single most important thing to take away is this. The entire point of training is to produce a set of weights. And the entire point of inference is to consume those weights. That's the handoff.
This table really spells it out. Training is this massive, crazy expensive, offline job that you do once in a while to create a set of weights. Inference, on the other hand, is what happens at runtime, constantly. It's where we load up those weights, take in prompts, and spit out tokens. As engineers building products, our world is almost entirely on the inference side. We care about latency, throughput, and cost. This is the part that's live.
Okay, so let's zoom in on that GPU runtime. When we say the model, what does that actually look like when it's sitting there in memory, ready to answer questions? At inference time, the model isn't some abstract idea. It's actual data sitting in your GPU's VRAM. And it's mainly four things. First, you've got the weights. These get loaded once and are shared by every single request coming in. Second, the KV cache. This is super important. It holds the unique state for each individual request. Third, you've got activations, which are basically temporary scratch pads used while computing each token. And finally, there's a scheduler, which is the traffic cop that batches and manages all the requests.
Let's double-click on that KV cache, because this thing is absolutely critical for performance. The attention mechanism in a transformer means that to generate a new token, the model needs to look back at all the previous tokens. The KV cache is a really clever optimization that stores the results of that looking back, the keys and values, for all the past tokens. This way, the model doesn't have to recalculate everything from scratch for every single token, which, trust me, would be incredibly slow. So here's the bottom line. There is a direct connection between the length of your context and the amount of memory you need. The longer the context, the bigger the KV cache for that specific request. This eats directly into your GPU's precious VRAM, and that in turn dictates how many requests you can handle at the same time on one machine. It's a fundamental trade-off you're always making. All right, now that we have all the pieces on the board, let's trace the entire life of a single user request, from the moment it hits our servers to the very last token we send back. So here's how it usually goes. A request comes in, hits an API gateway for things like authentication and rate limiting, then the inference service puts it into a queue. A tokenizer, usually running on a CPU, turns the text into those token IDs we talked about. The scheduler then cleverly batches that request with a bunch of others. The GPU does one big forward pass on that whole batch, then the system decodes the output to pick the next token for each request in the batch, and then it loops right back to step 5, over and over, until some stop condition is met. Only then is the final complete text response sent back. Even if your UI isn't streaming, this internal token-by-token loop is always happening. Now, that decode step, that's where you get to make a choice. The GPU gives you a score for every single possible next token. With greedy decoding, you just pick the one with the highest score, every single time. It's predictable, it's deterministic. With sampling, you use the probabilities from those scores to make a more random choice, which is how you get more creative and varied outputs.
Whew, all right, we've gone pretty deep into the low-level stuff. Let's just take a quick breath and recap the most important things to remember before we look at what's next. If you walk away remembering just 3 things, make it these. Number 1, LLMs at their very core are just next token prediction machines. Number 2, inference isn't a single action. It's a sequential token-by-token loop. And number 3, the reality on the hardware is a set of shared weights for everybody and a private per-request KV cache that gets bigger the longer your context is. So that leaves us with a pretty big question, right? We've just spent all this time going deep into the mechanics of how a single token is born inside the machine. But that's just one tiny piece of the puzzle. How do we take that core capability and build a useful, intelligent system around it? And that is exactly where we're heading next. In the next part, we're going to build on this foundation and start looking at the system around the model. We'll talk about things like tools, function calling, and we're going to walk through a full end-to-end support demo to see how it all comes together. Thanks for joining me.
Hey everyone, welcome back. In part 1, we really laid the groundwork. Today, in part 2, things get exciting. We're giving our large language models 2 incredible new superpowers: the ability to actually act in the world using tools, and the ability to know things from your private data using a technique called RAG. Let's jump right in.
So here's our game plan for this explainer. We'll start with giving LLMs tools, how that all works. Then we'll look at a real-world case study to see it in action. After that, we'll switch gears and talk about giving LLMs your data with RAG, and you guessed it, we'll wrap up with a real-world example of that too.
All right, first up, tool calling. You know, this is the magic that lets a language model, which is usually just trapped in a world of text, reach out and actually interact with the real world. It's how we turn language into action. It's how we give it hands.
So how does this actually work? Well, instead of just spitting out more text, the model can output a really specific structured command. Your application sees that command, goes and executes it, and then feeds the result right back to the model. This creates this awesome little loop you see here: prompt, tool call, execution, result, and then finally, the model gives its final informed answer.
Now, this slide gets to the heart of what makes this whole process safe and reliable: schemas. You can think of a schema as a super strict contract between the LLM and your code. It spells out exactly what a tool can do and what it needs to do it. This contract is what turns fuzzy language into something a computer can actually check. You know, letting you do things like enforce permissions and handle errors in a totally predictable way.
Let's make this feel a bit more real. Imagine we've got a support assistant for some kind of tech product. A customer asks, "My proxy started failing in Germany. Is it my account or the pool?"
Now, the model doesn't just guess. It looks at its available tools, picks the right one, and generates a perfect, precise function call to go get a real, factual answer. Okay, so let's walk through a full end-to-end example to see how this all strings together in a real support scenario. The key thing to remember through all of this is that the LLM is the planner, but your application is the one that actually does the work.
So it all starts here with the customer's request. They're getting these 403 errors, and they want to know where to even begin looking. Our application gets this message, and it sends it off to the model with a list of available tools, and basically says, okay, what's the plan?
And this is where it gets really clever. The model doesn't just try to answer the question, it comes up with a whole multi-step plan to gather facts first. It says, okay, first, let's search the knowledge base. Then, let's check the customer's account. Then, let's check the proxy pool health. And finally, let's check the unblocker status. It's thinking like a real support engineer.
So our application goes off and dutifully executes those 4 tool calls. And here are the results. The knowledge base gives some good articles, the account is totally fine, the unblocker is healthy, but aha, there it is. The proxy pool in Germany is degraded, and there's even an incident number attached. The model now has the ground truth.
Now that it has all those facts, the model can generate an answer that is incredibly precise and genuinely helpful. It tells the user their account is fine, points directly to the degraded proxy pool as the problem, and even gives them an immediate workaround. This isn't a guess, it's a data-driven conclusion.
This brings us to an absolutely critical rule when building these kinds of systems. Your tools are going to fail sometimes. That's just a fact of life. APIs time out, networks glitch. The golden rule is this: never, ever let the model turn a tool failure into a guessed conclusion. It has to know the tool failed so it doesn't just start making things up.
So what's the professional way to handle this? Well, first, if it's a safe operation, you can just try it again after a short wait. If that doesn't work, maybe you try a different tool as a fallback. And if all else fails, the system should know when to give up and escalate to a human, creating a support ticket with all the facts it managed to gather.
Okay, so we've given the LLM hands with tools. Now let's give it a memory. Let's let it tap into your private data. This is where Retrieval Augmented Generation, or RAG, comes into play. It's the go-to technique for letting an LLM answer questions using your own documents without having to cram them all into a prompt.
The RAG pipeline really has 2 parts. First, there's this one-time offline process where you prep your knowledge. You chop up your documents into smaller pieces or chunks, turn those chunks into numbers, we call them vectors, and store them in a special kind of database. Then, when a user asks a question, you do the same thing to their query, find the most relevant chunks from your database, and then feed only those chunks to the LLM to generate an answer.
Now, I gotta say, the quality of your RAG system is hugely dependent on how well you chunk your documents. I mean, it's quality in, quality out, right? Some best practices are to keep the chunks pretty small, always include headings for context, and attach lots of metadata, like what product or topic it's about. That stuff is super useful for filtering later. So you might be wondering, how does the database find the closest chunks? Well, it's all powered by a little bit of math. Basically, these embedding models map the meaning of your text to a point in space. The closer 2 points are, the more similar their meaning. A vector database is just really good at using formulas like cosine similarity to find the document chunks that are closest to your query's point.
Okay, let's put it all together and walk through our second real-world demo. We're going to see how the RAG pipeline can answer a really complex, specific question that a regular LLM would have absolutely no way of answering on its own.
Here is our customer's question. It is super nuanced and very specific to our fictional company's products. They want to know why their fancy unblocker product works just fine, but their standard proxies are getting blocked with a 403 error. The first step, of course, is retrieval. Our app takes that user query, turns it into a vector, and searches the database. You can see here it's asking for the top 8 most relevant chunks, and it's using that metadata we talked about to filter the search to only include docs about the proxies and unblocker products.
And here's what the database comes back with, the key themes from the documents it found. The chunks explain that the unblocker does way more than just change an IP address. It actually mimics a real browser. They also explain that raw proxies only change the IP, and that modern websites look at way more than just your IP to see if you're a bot.
So these retrieved chunks are now injected right into the prompt as context. The LLM's job isn't to use its general knowledge, it's to synthesize these specific facts into a clear answer.
And that's exactly what it does. It explains the core difference between the products and gives real, actionable advice based only on the information it was just given.
So let's just take a step back and recap. We've given our LLM hands with tools, which turn language into action. And we've given it a specialized memory with RAG, which retrieves knowledge to ground its answers. But what happens when you combine them? What happens when a model can use RAG to learn and then use tools to act on what it learned, over and over in a loop? Well, that's when you get into the world of AI agents, and that is exactly what we are going to dive into in Part 3. I'll see you then.
Hey everyone, welcome back to our AI crash course. In this part, we're leveling up from just talking to chatbots. We're going to dive deep into AI agents. These are systems that can actually plan, act, and solve problems pretty much on their own. We'll break down what makes them tick, see how they're starting to revolutionize coding, and help you get a handle on the tools that are out there today. Let's get right into it.
So here's what we've got on tap. First, we'll define what an AI agent even is and how it's different from a chatbot. Then, we'll see a really practical example of one in action. After that, we'll get into the nitty-gritty of how coding agents work and a super important protocol called MCP. And to wrap it all up, we'll take a tour of the coding assistants out there so you can make sense of all your options.
All right, first things first, what is an AI agent? The whole game here is shifting away from simple, one-and-done answers to something that's way more dynamic, something that can run by itself.
And this really says it all. On the left, you've got your standard chatbot. It's a one-shot deal. You ask it something, it gives you an answer. End of story. But on the right, you see the agent. It operates in this continuous loop. It makes a plan, it takes an action, it sees what happened, and then it revises its plan based on that outcome. And it just keeps repeating that cycle until the job is done. It's a huge difference. So what's the magic formula here? Well, it really boils down to these four things. You've got the LLM, which is the brain, doing all the reasoning. You've got tools, which are its hands, letting it actually do stuff like run a script or call an API. Then there's the control loop, which is the conductor orchestrating that whole plan, act, observe cycle we just talked about. And finally, and this part is absolutely critical, you have state. State is the agent's memory. It's how it keeps track of what it's tried, what worked, what didn't, and what it needs to do next.
You probably hear the word agentic being thrown around a lot lately. The key thing to know is that it's not some fancy new type of model. It's just a pattern, a way of putting things together. It means the system can run multiple steps, use tools to get things done, and, importantly, adapt based on what happens, all without a human having to constantly hold its hand. So when you hear agentic, just think LLM plus a little bit of autonomy, plus tools, plus a way to verify its work.
Okay, theory is one thing, but let's see how this actually works. We're going to jump back into that fictional SaaS company we've been using. But this time, the system is a full-blown agent that can run through multiple steps and make its own calls.
So check this out. We're giving the agent a really high-level goal. We're not telling it how to do its job, we're just telling it what we want. We're saying, hey, there's a spike in 403 errors. Either fix it, or if you can't, make sure you escalate it to the engineers with all the right info.
And just from that one sentence, the agent comes up with this whole 5-step plan all on its own. First, it's going to confirm the problem in the monitoring system. Second, it'll dig into the logs to see what's going on. Third, if it's seen this before, it'll just apply the fix. Fourth, if it's a brand new problem, it'll gather up all the diagnostic data. And finally, it'll create a ticket for the engineers with everything they need to know. That's its whole strategy created on the fly.
And here's where it gets really cool. We can see the agent actually executing that plan. It observes the error spike, so its first action is to run a log query. The result? It observes the logs are all pointing to an invalid token type error. Okay, new plan. Its next action is to search the company knowledge base for that error. The observation from that search is nothing. There's no known fix. So the agent knows it can't solve this itself. Its final action? Create a ticket and hand it off to the engineers with all the info it just found. And just like that, its job is done.
Okay, so we've seen it work for a support issue. Now let's take that same core idea and apply it to something way more complex, writing and fixing code. Coding agents use the exact same principles, but their tools and their whole world are focused on a code base. The absolute heart of a good coding agent is this thing called the verifier loop. This is its bread and butter. It starts by reading the code to get its bearings. Then it proposes a change, usually as a patch file. And now for the most important step. It runs verifiers. We're talking tests, type checkers, linters, anything that can automatically tell it if the code is any good. If something fails, it doesn't give up.
It looks at the error, tries to fix its own code, and runs the loop again. It keeps doing that until everything passes. Only then, when all the checks are green, does it finish up, maybe by opening a pull request. Without this loop, the agent is just, well, it's just guessing with confidence.
And to make that verifier loop happen, the agent needs a toolbox. Here's what's usually in it. You can see how these tools map directly to the steps we just saw. You've got tools to understand the code, like read file and search repo, a tool to actually change the code, apply patch. Then you have the all-important verifier tools, run tests, run linter, and run type check. And finally, tools to wrap things up like committing the code and opening that PR.
Now, there are a few different ways to build these agents. You have the basic React pattern, which is great for simple tasks. There's also a plan and execute pattern, where it figures everything out up front, which works for really predictable jobs. You can even get fancy with multi-agent systems, where you have different AIs playing roles like planner, coder, and reviewer. But honestly, for real-world, day-to-day software engineering, that verifier loop we just covered is by far the most practical and reliable way to go.
So we've established that agents are pretty useless without their tools. But how does an agent actually know what tools are available and how to use them? That's where something called MCP, or the Model Context Protocol, comes in. You can just think of it as the standard plumbing that connects an agent to all the tools it can use.
The flow is actually pretty simple. On one side, you have the agent, client. That could be your code editor or wherever the agent's brain is running. On the other side, you've got a bunch of tool servers that offer up abilities, like running tests or creating tickets. MCRP is just the standard language that sits in the middle and lets them talk to each other without having to know all the messy details about how the other one is built.
So what exactly does MCP standardize? Really, it's just three things. First, discovery. It's how an agent can ask, hey, what tools have you got for me? Second is execution. It provides a standard way to call a tool using clean, structured JSON. And third is the response. It defines how the tool reports back what happened. Remember, MCP is just the plumbing. The agent's brain is still making all the big decisions.
Let's make this super concrete. Remember our support agent? The first thing it does is send an MCP request to see what's possible. The method is just mcp.list_tools. The tool server then replies with a list of all the tools it has, and you can see right there, one of them is called create issue.
Okay, now that the agent knows the create issue tool exists, it can use it. It sends another MCP request, but this time the method is mcp.callTool. It specifies the tool it wants and then fills in the parameters based on what it learned, a title for the issue and a body with all the diagnostic info. And finally, the tool server does its job and sends back the result. The response shows the status was a success and even includes the URL of the brand new issue it created. Now the agent can see this result and know that its task is complete.
All right, let's bring this all back to what you can actually use today. We've gone through the theory of how coding agents work, so now let's look at the major players in the coding assistant world and talk about how to choose the right one for you.
This gives you a pretty good lay of the land. You've got the big one, GitHub Copilot for Microsoft, which is just so deeply integrated into VS Code. Then there's Google with Gemini Code Assist, which is really aimed at big companies using Google Cloud. The actual model makers, like OpenAI and Anthropic, are the ones pushing the envelope on these advanced agentic workflows. Of course, Amazon and Apple have their own assistants tightly woven into their ecosystems. And then you've got interesting new players like Cursor, who are building an entire editor from the ground up to be AI first.
Now, when you're using any of these tools, it is so important to know the difference between what I call vibe coding and real engineering-grade work. Vibe coding is awesome for getting a quick start or just sketching out ideas, but for code that's going into production, you need more. You need deterministic checks, tests, type checkers, linters. You need small, clean diffs that a human can actually review, not huge dumps of code. And you need those aggressive verification loops we talked about to catch bugs before they ever see the light of day. And if you take away just one thing from all of this, let it be this. This is the golden rule. Real productivity in software development with AI comes from combining fast generation with strong verification. Let the AI generate code super fast, but then be relentless about verifying that it's actually correct. So there you have it. From simple loops to complex coding, that's a snapshot of AI agents today. We've seen that the real magic isn't just in making stuff up, but in creating these autonomous systems that can actually check their own work. The real question now is, what amazing problems are you going to solve by giving an AI a goal, a toolbox, and the freedom to try, fail, and try again? Thanks so much for tuning in.
So that's the whirlwind tour. We went from the basic token loop all the way up to complex coding agents. I think the big takeaway is that these LLMs aren't magic black boxes. They're components that we, as developers, can wire into much larger, more powerful systems. Anyway, I hope this was helpful, Itzik. Let me know if you want to do a deeper dive on any of this stuff. Tools, RAG, agents, whatever. Talk soon.